Hello, everybody. I hope everybody is fine. And in this video, I'll go with partial wave analysis, and this partial wave analysis is used to basically decompose a wave function into components with some definite value, and this 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 partial wave analysis is uh, it's exclusively used to have some state of understanding of the scattering process when we have a probe. That probe is approaching to a target and interacting with the potential of that target. So what seems to be important here is that what it does basically is it decomposes a wave function into its components with some definite angular momentum. Now, what does this do with us? This allows us to analyze the scattering process more effectively by basically focusing on the contributions from different angular momentum states. And these angular momentum states are labeled by the angular momentum quantum number L. Now let's go through this partial wave analysis and see how it works and where from we have to start. Now, the starting point for this partial wave analysis is basically our time-independent Schrodinger's wave equation for a particle that's moving in a potential, say, V of r. So time-dependent Schrodinger wave equation. Okay, so if I write down the Schrodinger's wave equation, 2m, then I'll have del square plus V of r psi of r equals E psi of r. So we can, as we have already done in our previous course, we have worked out the problem of Schrodinger's wave equation in spherical polar coordinates, preferably when we have discussed the problem of hydrogen atom. So we can write down this Laplacian in spherical polar coordinates. Laplacian in spherical polar coordinates. So we can write down this Laplacian as del square is 1 by r square dou by dou r of r square dou by dou r psi of r is E psi of r. So this is our Laplacian in spherical polar coordinates, and something is missing here. Yeah, it has to add the angular momentum here, so plus, so it's L into L plus 1, and L is an orbital quantum number, so I can write down here as L square. Okay, I can write down L square 1 by r square. So where this L square is, it's the angular part of this Laplacian operator, and this is our angular momentum operator. Now what we do is we assume that we have a wave function, and this wave function, so we have a wave function psi of r here, and this wave function can be separated into the radial part and angular part. So for that, so this psi of r is basically r of r, and y, l, m, and theta and phi. Everybody is aware about it, and where this y, L, M, theta, phi is what we call them. We call them spherical harmonics. We call them spherical harmonics. All right, and these spherical harmonics, what they do is, what was our spherical harmonics? So we have y, L, M, and as a function of theta and phi, and these are our spherical harmonics. And what they do is they describe the angular dependence of the wave function. So this is angular dependence of wave function. And we have this this M, we know this is magnetic quantum number, and this L is the orbital angular momentum quantum number. So this M is our magnetic quantum number, and L is orbital angular momentum quantum number. And if we go with the radial part of, suppose what we have now, we have psi of r as a function of r, and spherical harmonics, theta and phi. What we do, we substitute this thing in our Schrodinger's equation, and we have the Schrodinger's equation. And what we do, we know all that process. We make use of, we separate the variables. We use separation variable technique. We separate the variables, and when we separate the variables, what we get is, we get two equations. One is our angular equation, and the another one is radial equation. So these two equations we obtain, and we better remember exactly how we boil down those separate equations, and connect them using some fundamental constants, like the quantization of angular momentum. So for angular equation, what we have, angular equation, and the angular equation, what it does, basically, it gives us the spherical harmonics. We obtain spherical harmonics, and which are basically the eigenfunctions of angular momentum operator. They are basically the eigenfunctions of angular momentum operator. So these are our spherical harmonics. And what's that? That is L operator, Y, L, M, and theta, phi. This is, what is that? L into L plus 1, then Y, L, M, theta, and phi. So that's fine. Okay, that's beautiful. And then we have the radial part, and in radial part, what we have R of R. So this is our angular part, and then we can write down this radial part. So that is minus h cross square by 2m 1 by r square d by dr of r square d by dr plus h bar square L times L plus 1 divided by 2m r square plus V of r, and this whole thing that we have is multiplied by r of r. This r of r is linked to our wave function, and from here what we have, energy eigenvalues, E r of r. I don't know whether it's visible. Yeah, it must be. So these are the two important parts that we obtain, and by using separation of variables to the Schrodinger's equation, while we incorporate Laplacian operator, and we obtain the the spherical harmonics, and the spherical harmonics are basically the eigenfunctions of angular momentum operator. And from there, what we get those uh, quantized values of angular momentum quantum number. And then in the radial part, we have a radial equation, and from there we get the energy eigenvalues. So this is our angular momentum equation, and this is our I should call it the radial Schrodinger's equation, and this equation governs the radial part of the wave function. Now, what is important here is that we have the asymptotic behavior. Now, uh, we, we exploit the asymptotic behavior and link it and link it to our partial waves. So what we have the plane wave, and this plane wave is modified when it interacts with the field of the target. Now, if we assume that our situation is asymptotic, so what does asymptotic mean? If I take this R tending to infinity, and if R is tending to infinity, this R is tending to infinity, that means V of R should vanish. It should vanish, and the solution will become it becomes a free particle solution when R tends to infinity. And the radial equation for the free particle in the asymptotic region, so this is our radial equation that we have written down. So V of R is dead, it's gone in this approximation. And using a solution like U of R equal to R and RL of R, we obtain the equation like D2 U1 of R. So it's UL, I should call it. So this is UL of R divided by dr2 plus k square minus L into L plus 1 divided by R square. And here I'll have UL of R equal to 0, where this UL of R is taken as the function of R and RL of R. And the K that I have introduced here, this K is over the same thing as we know, 2me by h bar. All right. So this will be our equation. Now, so this is the asymptotic solution when we assume that R is infinity. Then this V of R that's appearing in our Schrödinger equation, it vanishes, and you boil down your equation to this format. Now, so for large R, the solution is now, if I have to write down the solution of this differential equation, the solution is linear combination of, if I go to the more general way of dealing with this problem, the solution is basically the linear combination of Bessel function and Newman functions. So if I write down the solution of this equation, so the solution is basically the linear combination of, so UL of R is nearly, I should call it nearly, ALJ L of KR plus BL, then NL K of R. So where this solution is from Bessel functions, and this is the solution that comes from Newman's function. Now, in scattering theory, what we do is we typically apply the boundary conditions, and we apply those boundary conditions at large distances. And see the role of perturbation to inculcate ourselves in the problem of scattering. So we are trying to reach we are trying to start our solution from an ideal situation. So what we do here is that we apply boundary conditions at large distances, where the wave function consists of an incoming, as if there is an incoming wave, and this incoming wave is a plane wave. It's a plane wave, and an outgoing. So when it goes from, suppose this is the target potential, and an outgoing spherical wave. Spherical wave. So you have a plane wave in a mathematical sense, and this plane wave has modifications when it interacts with some kind of potential, and you have you come up with a spherical wave. And the asymptotic form of this radial wave function can be, at large distances, you can approximate this for sake of understanding as 1 by kr sine of kr minus L pi by 2 plus delta L. So we are interested in the physics of our problem. So when you boil down UL of R and you use your boundary conditions for large R, you come up with this equation. And in this equation, the point of importance is this delta L. And what's this delta L? This delta L is phase shift. It is phase shift for partial wave with angular momentum L. So I wrote it badly. This is delta L, and we can encode the effects of the potential on the scattered wave, the wave that has been scattered. Now, the total wave function at large R is given by the superposition of this incoming wave and the outgoing wave. So there is superposition between the waves. Now, in the case of an incoming plane wave, what I have, I can think of incoming plane wave as I can think of it as e to the power of iota kr, and yeah, and outgoing wave in asymptotic region can be written as the sum over all these partial waves. And in that case, the psi of r is nearly, it's the superposition, so 2l plus 1, then I have I, and then I have e to the power of I kr by r pl cos theta times 1 plus 2i delta L. So this is our situation here, and I have e to the power of I kr, all right, and divide by r, and then pl cos of theta, and then 1 plus 2i delta L. Now this pl cos theta, all of you know, is nothing but Legendre polynomial. Legendre polynomial. And the scattering amplitude from this equation, the scattering amplitude is related to this phase shift. And it is related to our phase shift. And what is that? That is scattering amplitude. What is that? That is f of theta is sigma L equals 0 to infinity 2L plus 1, then e to the power of I delta L sine delta L by k. and PL cos theta. Now, in this equation, the point of importance is the delta L. That gives us the phase shift, and phase shift is only when you have an interaction between the incoming wave and the potential that's surrounded by that. And from here, f of theta is our scattering amplitude, and we can write down the differential cross section. So what is differential cross section here? That's square of f of theta. So magnitude of differential cross section. Differential cross section, that is d sigma by d omega. So that is f of theta whole square. So where we know that this sigma is the total scattering cross section. Total scattering cross section. Now let's go with the physical significance of these phase shifts, because the physics lies in those phase shifts. And our phase shifts are delta L. Now this delta L, it characterizes the potential modification. It modifies the free particle. You have a free particle, which is a wave, interacting with some potential, and it gives me the measure of that modification that comes in action when it interacts with the potential. So I should say that the phase shift delta L characterizes how the potential modifies the free particle wave in each partial wave, because you have a long range of waves that are associated with the particle, because a particle is a group of waves. So the value of this delta L determines the scattering amplitude for the given angular momentum. Okay, so all you need for given L and for given delta L. So this delta L is basically giving us the scattering amplitude, because the scattering amplitude has a dependence on delta L in its exponential function. And if, for example, if I say that this delta L is 0, what does that mean? That means no scattering has occurred. There is no scattering for the partial waves. And if this delta L is large, what does that imply? That implies there is significant amount of scattering for that partial wave which is interacting with the potential. So to summarize this video, I should say that in practice not all partial waves contribute equally. So if you have partial waves, they don't contribute equally for low energy scattering, and the contribution from higher values of L that we have are often negligible. They are small because these values are small. For large values of I'm talking about, sorry, I'm missing it. I think for low energy, if we have less energy of scattering taking place, the contribution from the large values of these L's, their contribution is less. So thus we can say that the analysis can be truncated at reasonable values of L. So L has to be reasonable. L cannot be large. It cannot be large. That's why this partial wave analysis it is confined to, I should say it's confined to L is equal to 0 and L is equal to 1 states. So L is equal to 0 refers to our S state, and L is equal to 1 is the P state. So it doesn't go beyond 0 and 1. Because in that case we have we have the centrifugal barrier. We have centrifugal barrier if delta L is large and L is large. So, to step down, what we did basically here is we have begun with the Schrodinger's equation, and we used the separation of variables to split the wave function into the radial and angular part, and we wrote down those equations, and uh, and we wrote down the solution of the radial equation considering the asymptotic behavior at a large distance, and we expressed the solution as combination of Bessel and Neumann's functions, and we imposed the scattering boundary condition to determine the phase shift delta L, and we use the phase shifts to compute the scattering amplitude, because it is the phase shift that is going to give us the measure of scattering amplitude. Once we are able to measure the scattering amplitude, we can easily measure the differential cross section, and we have tried to interpret the physical significance of this delta L, and and what is important here is that sum over partial waves to get the total scattering amplitude. So because we are calculating the total scattering amplitude, that's why we have been introducing here sigma. So sigma takes care of summing up all the partial waves under consideration to calculate the scattering amplitude. And this is how it goes. And at the same time, if I go back, see what we used here is the asymptotic solution, and the asymptotic solution is we use it only when we have large distance between the 2 points of contention. And this asymptotic solution at large different distances, it refers to the behavior of wave function or a physical quantity. It's not essential that you will only talk about the wave function, as the distance from the scattering center becomes very large. So you have asymptotic solution only when the distance from the center of the potential to the point where your wave is. When it is large, then you can look for those asymptotic solutions, because at large distances, the potential, the magnitude of potential is negligible. And in scattering theory, understanding the behavior is crucial for analyzing how particles interact with these potentials. If we are not able to understand the behavior, then we cannot say anything about it. So asymptotic solution describes basically how the system behaves at extreme limits. Taking this point to the extreme point, it's not totally independent, but still it is at an extreme point. And specifically, if here we have to talk practically, then practically this R tends to infinity. And in the physical context, again, in scattering problems, we are often interested in how the incoming wave, like a particle that is coming, and if this particle has a wave function, and how this wave function interacts with the potential, the target potential, and how this wave is altered, how this wave is modified by this potential. And this is how it works. This is how asymptotic solution is taken into account. So with this, I would like to tell you bye.